Hello everyone. Our senior design topic is high-efficiency microinverter for PV panels. Our team consists of Yi Guo, Wenxi Yu, Yu Yan, and Yunpeng. Our advisor is Professor Natu. I will develop my presentations basically in two phases. First comes the introduction. Next is the main circuit. Third is a control strategy. Last but not least is the results. Here I will give some basic introductions of our whole systems. Recently, the concerns for the environment has been increased ever since, so there has been an increasing interest in natural energy. We are interested in transforming solar energy into electrical energy, which is seemingly the most conspicuous energy in the world. Our whole system is basically consisting of several subsystems. Here are some system standards for our whole design. IEEE 519 and IEEE 1547, EN 61000-3-2, and National Electrical Code 690. The maximum output power is supposed to be 200 volts, and the MPPT factor is supposed to be above 95%. Our nominal output voltage should be 110 volts for single grid, and the nominal output frequency are supposed to be 60 Hz. The output frequency range should be between 57 to 63 Hz, and the power factor should be above 0.95. The total harmonic distortion should be smaller than 2%, and the system efficiency is supposed to be over 90%. Some parts of our main circuit. Our main circuit is consisting of flyback converter, a full bridge inverter, a flyback drive circuit, a full bridge drive circuit, and an EMI filter. And the corresponding control circuits are consisting of a DSP IC33FG 60JS405, an AC current sense, an AC voltage sense, and flyback current sense, a flyback voltage sense, and a PV voltage detector. Here you can see an overview of our whole system. Basically, we use several Radio Shack boards to build our homemade PCB board. At the very beginning, we kept the option open to choose different strategies. And last, we chose a flyback converter because it will boost voltages with fewer components and with a galvanic isolations. But it's actually a trade-off because we may have lower efficiency, and the primary side of the converter transformers will possibly be saturated. Next comes the flyback converters. Here is our board of the flyback, a pair of flyback converters. They're called interleaved flyback converters because they are actually phase reversal. This topology is used basically to reduce the ripples and to increase the power factor. These five are five decoupling capacitors in parallel, also to reduce the ripples. And these are the pair of transforms. They are phase reversal. And here are a pair of Hall effect current sensor, whose output is a current of these two transformers. And here is our full bridge inverter. You can see the different drive signals of our inverter. Next is a control strategy. Basically, we will have three methods to control the whole system: current control, MPPT control, and PLL control. The current control is aimed to generate PWMs, and the MPPT control is basically to generate the maximum power, because in different conditions, we have different curves of the input voltage and currents of the PV panels. And as for PLL control, we're trying to make the power factor to become unity. Here is our MPPT control methods. Basically, we're trying to set the working condition at this point, which will yield the most energy. And for PLL control, the full name of the PLL control is called phase lock loop. It's basically to keep the output current in phase with grid voltage, namely to keep them synchronized. And in this way, the power factor is kept to be unity. For the controlling methods, we will get the grid voltage amplitude and the grid voltage phase. Then we will generate a current reference. And then next comes a current control. After this, we will have different PWM duty cycle, which tends to be time shifting. Here is an overview of our physical circuits of the controlling circuits. And then comes the PSIM simulation result. Here is how we build the whole system in PSIM. And this guy is a reference voltage that we are supposed to get as an output current. And this guy is what we got as a real output in PSIM. Also, this guy is a ideal flyback output, and this guy is a physical one. Here is a graph of our final output. Also, the above one is the ideal one, and the below one is a real one. Here is some of our conclusions. First of all, we were supposed to join an IEEE IFAC competition, but because it's due June, we may not have so much time to design the whole PCB. So we choose the Radio Shack boards to build our whole system, and also for the subsystem testing. And we use some grid connected protection devices but I think we still have some work to do to improve our protection circuits. Also, we need to improve system tolerance for high voltage and large current. And we also has to develop a method to keep the fitness for various solar energy conditions. And finally, we need to improve our system efficiency. Any questions? And that's all for my presentation. Thank you all. Our design is called high efficiency microinverter for photovoltaic panels. To be more specific, we collect the solar energy, transform it into AC voltage, and feed it back into the grid. Basically, our whole system consists of 3 subsystems: a pair of interleaved flatback inverters to convert DC to AC, a full bridge to unfold the sine signals, and last comes the EMI filter, together with some voltage and current protection and sensor circuits. On the left side lies the main circuit, while the right side the DSP and feedback loops. The microprocessor uses a zero detecting and phase-locked loop to generate time-shifting duty cycle PWM signals to drive MOSFET switches, thus controlling the feedback converters and the full bridge to make the output synchronize with the grid. Sensors and protection circuits are made to ensure each stage are working properly. Okay. This is the software we use to write the codes into the DSP. And this is the schematics of our DSP. You can see it from microchip. And we have different pins and the functions on it. We connect the laptop to the DSP in our system. And now we will write the codes into our system.
Okay, so here's what happened. I think there was 2 NPNs, okay? But Adrian said that when he showed it to him, he complained.
You can see that the code has been successfully written into our DSP. Now, these are our subsystems. First of all, we used 2 DC sources in parallel to provide a large range of input currents. We connect these 2 DC sources together and connect it to the input as a solar panel input. And these guys are a combination of a transformer and an auto transformer. We connect it to the grid, so the outcome of this should be a smaller AC voltage. It's just a model of the grid. And finally comes this guy. This is a power supply of all of our chips. It will provide with 12 volts, 5 volts, and 3.3 volts analog signals. And last but not least, we use the different channels of the scope. The channel 1 is connected to the grid, the grid model, basically the outcome of this guy. And we use the channel 2 to connect to the output of our system. We have connected the transformer to the grid. Now we are turning on the PV panel input and then power supply. Okay, here in the picture, you can clearly see our final output. In the picture, the yellow curve is a grid model voltage, and the green one is our final output.